Okay, today we are in day 6 notes, and day 6 starts with chord segments. So everybody turn to page 12, and we'll get started on chord segments. When you look at two segments or two chords that intersect, you'll notice that when they intersect, they divide each other into two parts. These are called chord segments. So C to E is a chord segment, E to D is a chord segment, A to E, and E to B. When two chords intersect, in order to find the length of them, we can take the length of CE times ED. So CE, I'm going to write it down here. Let's see. Let me grab my blue for North Carolina. CE, segment CE, times segment ED, and that will equal segment AE times segment EB. Okay, and that's called the segments of chords theorem. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So this chord segment times this chord segment equals this chord segment AE times this chord segment BE. Okay, a secant segment is the part of the that contains the chord and the part that's outside of the circle. So yes, it cuts through the circle. And how can we find the lengths of a secant segment? And this has a theorem also. If we take AB, which is a little different than the chords, if we take AB, the outside part, times the whole AC, it will equal, in this case, a tangent squared. Okay, so this is what a secant segment and a tangent look like. Let's go to the segments of secant's theorem. This one says if you take the outside portion, EA, times the whole portion, it looks like EB, it will equal the outside portion of the other secant segment times the whole secant. Okay, so I'll write this down. Outside is EA times the whole E to B, and that will equal on the other secant EC, the outside, times the whole E to D. So when you have an outside, that's how I think about it. Outside times the whole, don't forget, not just the inside, equals outside times the whole. Okay, and that's how we find the lengths when we have two secant segments. Now sometimes we'll have a secant segment and a tangent. So the secant segment is the same. Outside times the whole equals, and we don't have an outside or a whole here, so we take that tangent and multiply it by itself. So in our case, it will be EC, the outside, times the whole, ED, equals EA squared. So E to C times E to D, the whole, will equal EA, the tangent, squared. Okay, so let's do some practicing here. I see two chords that intersect, so I see two parts on AC and I see two parts on BD. So I'm going to take the 3 times the 8, and that will equal the 4 times the x. Or 24 equals 4x, and when I divide both sides by 4, I find out x is 6. Let's go over here to B. I see a 4 and I see a 4. Oh, 4 times 4 will equal 5 times x. 5 times x, or 16 equals 5x. And when I divide both sides by 5, I get 16/5, which is the same thing as 3.2, I believe. Okay, again, we have two chords intersecting. So 3 times 8 will equal 2 times 3x. 2 times 3x. So we have 24 here, and 2 times 3x gives us 6x. So when I divide both sides by 6, x equals 4. And on D, we have two chords intersecting. It looks like x and x. So on one chord, I have x times x, and on the other chord, I have 4 times 9. So I have x squared equals 36, and when I take the square root of both sides, x equals 6. Okay, here I have two secant segments, so I have to be careful. I want the outside times the whole. So I'm going to add up both of the segments to get the whole. So on AC, I have outside is 4, and the whole is 6 plus 4, or 10. And that equals 5, the outside, times the whole, which would be 5 plus the x. So 4 times 10 is 40. Have to remember to distribute here. 5 times 5 is 25, plus 5 times x, 5x. Subtract your 25 from both sides, and we'll get 15 equals 5x. And dividing both sides by 5, x equals 3, or 3 equals x. Okay, this was an outside times the whole. Same thing with F. The outside times the whole will give us outside, and the whole line will have to add those parts together. 4 plus x equals the outside of the other secant segment times the whole, which is 5 plus 4. So distributing this 4, I get 16 plus 4x equals, and 5 times 9 is 45. Subtracting 16 from both sides, I'll get 29. Dividing both sides by 4, x equals 29/4. Let's see, that will go in there, 7 times. Oh, I better just leave it as 29/4, because that can't be reduced. We'll just leave it there. Okay, two secant segments. Outside times the whole will be 3 times 3 plus 6, which is 9, which equals x, and the whole line would be 2 of those x's. So 3 times 9 is 27, and x times 2x is 2x squared. This is kind of a tough one, because if I divide both sides by 2, I'm going to get 13.5 over here, which equals x squared. And now I need to take the square root of both sides. So I think I'll just leave my answer like that, because that is not a perfect square. But x equals the square root of 13.6. So you can go ahead if you want to and put that in your calculator, and you'll get an approximation there. On H, my outside is 1, my inside is 2x. So outside times the whole. Remember now, we cannot add these two parts together. So we're going to just write them. 1 plus 2x, that would be my whole, adding those together. And that equals the outside times the whole. Now those two I can add together to get 5. 1 times 1 is 1, plus 1 times 2x is 2x. And on the other side, 1 times 5 is 5. Subtract 1 from both sides, and we have 2x equals 4. And dividing both sides by 2, x equals 2. Okay, here we go with a secant segment and a tangent. Remember, the tangent gets squared. So I'm going to square the 2x. And that will equal my outside times my total, or 9 times 9 plus 4, which is 13. Now when I square 2x, I have to square the number and the x, so I'm going to end up with 4x squared. 9 times 13, let's see, 9 times 3 is 27, so that gives me 117. Let's see if we can divide both sides by 4. So we could get x squared equals, let's see, 4 goes into 11 twice, 37 left over. Holy smokes, that's not going to work. So 117 over 4, and we need to take the square root of both sides. So x will equal the square root of 117 over 2, because I can take the square root of 4. And you can put that in your calculator if you want to get an approximation. Okay, on J, we have a tangent and we have a secant segment. So on J, we're going to square our tangent, which has a length of x, and that will equal the outside, 4, times the total, which is 4 plus 5, 9. So we know x squared equals 36, and taking the square root of both sides, x will equal 6. Okay, now when we get to K, we're on the last two problems here. Again, tangent, secant. Tangent gets squared. Secant is outside times the total, 5 plus 6, 11. So x squared equals 55. Taking the square root of both sides, x equals the square root of 55, which cannot be simplified, by the way. It's 5 times 11. But you could go ahead and put it in your calculator and get an approximation. Okay, on our last one, we have a tangent, which we'll square, and we have a secant segment. So we'll take the outside times the total. So we have tangent squared equals the outside times the total secant segment, 12 plus 4, which is 16. So we have x squared equals, and 12 times 16 is 192. Okay, we had this number before, and we want to think about any perfect squares that will go into it. Let's see, 4 goes into it. So, because 4 goes into 92, so let me start there. 4 is a perfect square. 4 goes into 19, 4 times, 3 left over. Bring down the 2. 4 goes into 32, 8 times. Oh, well, 16 goes into 48, and it goes in there 3 times. So I have 2 perfect squares, and what this means is when I'm taking the square root of 192, it's the same thing as 4 times 16 times 3. 4 is a perfect square, so it can break out of jail. 16 is a perfect square, so it can break out of jail. So the square root of 4 is 2. The square root of 16 is 4, but the 3 has to stay in jail. The square roots come out in front, and I multiply them times each other, and I find that x will equal 8 square root 3. Okay, time to start on your homework, worksheet number 6 today.